Hey there, we are members of the UC Berkeley MSOL lab and representing APHIS. And today we're going to talk to you about some of the cool things that we're doing in our lab with regards to agricultural production. So here we have a satellite image of farmland. And as you're looking at this image, you may notice differences between farms from this bird's eye view. But if you pick out even just one of these farms and look closely, you can actually see that there's some variation within a single farm field. Now, this is not because of cloud cover or some trick of the camera. There really are differences there. And that difference in color that you're seeing is the result of soil variation. And from this view, it's apparent that soil properties vary across distances smaller than even a single farm field. These differences in soil properties can have a big impact on crop health. With that in mind, how granular of data do we need to collect in order to capture these differences? In other words, if we place a sensor in the field, how far away would we need to place another sensor to have geostatistically accurate results? Interestingly, different soil properties vary more or less radically at different scales. In recent years, researchers have tabulated the distances that you would need to measure to account for these differences, several of which are shown here on the table on the left. But industrial commercial farmers rarely account for this granularity when making decisions regarding how to manage their fields. What would it look like to have a farm operating with this level of granular feedback control? Well, we investigated this by coming up with an algorithm that places sensors in a field using these geostatistically accurate distances from the page before. And looking at this, looking for nitrate and soil moisture by distributing sensors in the field at this rate using some assumptions from other previous literature, we estimate that adopting a system such as this could save a farm up to $1,000 a year for the average center pivot farm.
Since these fields range in scale and usually are 100 meters in length, we need to find a way to efficiently scan all of these sensors, even multiple times throughout a growing season. For this, we will look into optimizing the flight paths of drones to traverse these farms to scan these sensors. The way we're modeling these drones is by an attraction and repulsion force similar to that of molecular forces, where they're attracted to the sensors that are laid out across the field, but then stay away from the obstacles. And if they get too close to an obstacle, they are eliminated from the simulation. But when they get close to a target, in this case, a sensor, it is considered mapped and it will go on to the next sensor. We optimize the attraction and repulsion forces for each drone, depending on if it's an obstacle or a target, using the genetic algorithms. With the genetic algorithm, we rank the string performance, create child strings, and replace costly strings to arrive to an optimized parameters for each drone. Further developing these simulations, we can add further functionality such as crop dusting and LiDAR mapping. In this video, we have 3 drones scanning a central pivot field, along with scanning each sensor. And if each sensor dings the drone to need more fertilizer, then it supplies a certain amount of fertilizer in that area.
So not only do we want to look at regular agricultural systems, but we also want to look at next generation agricultural systems, namely agrophotovoltaic systems. And these systems can be described as energy generating systems integrated with agricultural production.
And the motivation behind looking into this is because the agricultural land is limited, conventional solar panels do not incentivize switching to agrophotovoltaic production. So machine learning algorithms can be used to figure out the optimal panel position and activation of energy storage units depending on ambient parameters for certain objectives, such as plant growth, net energy usage, and reduced water usage.
We can also look at greenhouse systems in which land use efficiency can be maximized through optimized solar farm and greenhouse designs for location and plant-specific applications. And with that, those are all of the projects that we have been working on with regards to agricultural systems. Thank you for listening.